So for this deep dive, we've got this really fascinating stack of papers in front of us. They're out of the University of Pennsylvania and the University of Michigan from early 2026.
And they're tackling what's been, the holy grail for microrobotics for decades.
We're talking about fully autonomous agents, robots the size of a paramecium, maybe 200 micrometers long.
Yeah, and the mission here, what they finally solved, is bridging that huge gap between the brains, the microchips, and the bodies, the actuators that make them move.
A gap that's been the sticking point for, what, 20, 30 years?
Easily. You could always make a tiny chip or tiny actuator, but getting them to work together in one unit, that was the problem. Everything before this was basically a marionette.
Right, you have these little things being pulled around by, like, external lasers or magnetic fields.
Exactly. But these new bots, they've finally cut the strings. They are programmable, and they are autonomous.
To really appreciate what they've done, though, we have to talk about the environment. I mean, the physics at 200 micrometers is just bizarre.
It is. You're deep into what's called low Reynolds number territory.
Yeah.
And all the rules of our world, they just go out the window.
Water doesn't behave like water anymore, does it?
Not at all. For a robot this small, water feels thick, like pushing through tar or molasses. Viscosity is everything, and inertia is basically zero.
So if you stop pushing, you stop. Instantly. There's no coasting.
Dead stop. And that leads to another problem, something called the scallop theorem.
Ah, right. Where simple back and forth motions don't work.
They get you nowhere. You just wiggle in place. So any kind of simple hinge or flap is useless.
Which means mechanical parts, like propellers or legs, are completely out of the question. They just jam in the tar anyway.
Right. So the big breakthrough was to get rid of moving parts entirely. They developed what's called the electrokinetic propulsion system, EKPS.
And this is the really clever bit of physics. Instead of pushing the water mechanically, they're, grabbing it electrically?
That's a good way to put it. They use a voltage field along the robot's body to literally drag charged ions that are already in the fluid.
So by dragging the ions backwards?
The fluid flows,
Yeah.
and that pushes the robot forwards. It's momentum transfer. And because it's solid state, it's practically indestructible.
I read that you can shoot them through a micropipette.
You can. And they come out the other side working perfectly.
Okay, so that's the movement. But honestly, the compute power they packed in here is what really blows my mind. We're looking at a 55 nanometer CMOS processor.
Running on just 75 nanowatts.
Wait, say that again. 75 nanowatts. That's nothing.
It's 100,000 times less power than a standard smartwatch. It's barely a rounding error.
How is that even possible? They have to be using sub-threshold logic for that.
They are. Instead of fully switching a transistor on, which burns power, they're running it in the off state. They're computing with the tiny bit of current that normally just leaks through.
They're computing with the leaks. Wow, okay, so that creates a huge communication problem, right? You can't power a radio on leakage current.
No, absolutely not. RF is impossible. Input is relatively easy. You just flash lights at it like Morse code, and its solar cells pick that up.
But getting data back out?
That requires some very creative thinking. They looked at nature.
The waggle dance.
The waggle dance.
Yeah.
Just like a honeybee. The robot can't transmit a signal, but it can move its own body. So it physically wiggles left and right in a specific pattern.
Manchester encoding.
Exactly. A wiggle left is a 0, a wiggle right is a 1. You literally watch it dance under a microscope to read what it's thinking.
That is amazing. But, maybe the most disruptive part of this whole story isn't the tech itself, it's how they're made.
Because they're built on standard silicon wafers, right alongside normal computer chips.
Which completely changes the economics. What's the cost per unit?
About 1 penny.
1 cent. So we're shifting from robotics as, an expensive asset to robotics as a consumable.
Precisely. You don't send one precious robot. You can inject a swarm of 10,000 of them into a system.
Yeah.
If you lose a few hundred, who cares? It becomes a numbers game.
It's just such a massive leap from those 2020 origami bots that were just being folded by remote control.
Oh, yeah. These new agents can sense temperature changes down to 0.2 degrees Celsius, process the data, and then decide on their own where to go next.
And that temperature sense is the killer app for medicine, isn't it? Finding tiny points of inflammation before an MRI could ever see them.
The navigating between cells. It's a whole new world. We're basically flooding the microscale with cheap, disposable intelligence.
And I think that's the real shift to think about here. We're used to robots being expensive and rare, but what happens when intelligent agents are as disposable as a paper cup? How does that change how we solve problems inside the human body?
It's not about sending in one surgeon anymore.
It's about sending in an army of consumables.